Hello guys, welcome back to TechDose, and in this video we will look at delete duplicate folders in system problem, which is from Leetcode number 1948. A prerequisite before solving this is to learn about TRIE. You should know how to insert strings into a TRIE, how to build TRIE, and how to do searches in a TRIE. So I have already made detailed videos based on TRIE, and all the links will be present in the description below. So please go there and watch it if you don't know about TRIE. Another problem which you can solve after having solved this is serialize and deserialize a binary tree, which is from Leetcode number 297. Again, I have explained this in a lot of detail in another video. So this link will also be present in the description below. So please go there and watch it. Let's now read the problem statement. Due to a bug, there are many duplicate folders in a file system. You are given a 2D array paths where path set I is an array representing the absolute path of the ith folder in the file system. Absolute path always starts with the root node. So you can say that the absolute path of A will be /A, the absolute path of B will be /A/B, and so on. For example, 1, 2, 3 represents the path /1/2/3, where the first slash is actually the root node. Okay, so this is representing one path. Okay, so this is the path for folder number 3. Two folders not necessarily on the same level are identical if they contain the same non-empty set of identical subfolders and underlying subfolder structure. The folders do not need to be at the root level to be identical. If two or more folders are identical, then mark the folders as well as their subfolders. So I will be explaining this with the example given below. Okay, so I will not be reading this example. Let's skip and see the main logic of the problem. So once all the identical folders and their subfolders have been marked, the file system will delete all of them. The file system only runs the deletion once, and so any folders that become identical after the initial deletion are not deleted. Return the 2D array answer containing the paths of the remaining folders. After deleting all the marked folders, the paths may be returned in any order, right? Let's look at all the examples one by one. So if you look at the first example, how was this structure even built? If you look at the path A is saying that from the root node you have A. If you see C, then we are inserting C into the trie, starting from /. D, insert D. Then AB, go to /, then go to A, and then insert B. For CB, start from the /, go to C, and then insert B. Then for DA, go to /, go to D, and then insert A. This is how you do trie insert. So you can do trie insert using all the paths absolutely, and for each of them you have to start from the root node. So this is the root of the trie from where you can start for every absolute path and try to insert the nodes which were not inserted, and we have done that. Now after doing this, you have to identify the identical folders. Identical folders are such folders where everything below them are exactly the same. So if you consider A and C, everything below them are exactly the same. That means they should have same number of folders at the same level and exactly with the same name. Okay, so if you look inside A, you just have one folder with B, and inside C you just have one folder with B. So they are identical, and therefore this entire part will be removed. And after removal, you will just be left with DA along with the /. And that's why the answer has D and DA. That is the path to each of the folder, absolute path to each of the folder. Okay. Now if this C had, let's say, another A here. Okay, C had another folder A. Then in this case, A and C will not be identical, because below A there is B, which is only one count, and this structure is not the same as below C you have B and A. Yes, there is B, but you also have an extra folder A. So you have two items here. So the structure is not exactly matching. So in this case, there will be no duplicates. There will be no duplicates. Okay, so nothing can get removed. Even if you compare this D with A, you will find that C contains A and D contains A, but C also contains B, which is not contained inside D. If D had B here, then you can say that since D has AB and C has AB, then they both are identical. So remove them and the answer would be /AB, right? So I hope it is clear. Now if you look at the second example, the matches may not be at the same level. They can be at different levels. So here you will see below X and below W, you have the exact same structure, and that is why they will be removed. They are not at the same level, right? Now let's say that they are removed. After this AB and this CB will match. Okay, they will match, because inside A you just have B and inside C you just have B. But the problem says that your cleaner, that means the deletion, will only happen exactly one time. So if the deletion had happened one time, even though A, B and C, B structures are matching, they cannot be removed because this was not happening in the first time, right? So that is why your answer will contain C, CB, A, AB. You see, C, CB, A, AB. It can be in any order. You can write A, AB, C, CB, or A, C, CB, AB, whatever. The order do not matter. Now, in the next example, you will see there is nothing in common, and therefore this trie will remain the same. So all the paths remains the same. Okay, nothing can get deleted. So I hope the problem statement is clear. Once you have seen the problem, let's now look at the constraint. In this case, the paths.length, let's call it n. That means the number of folders that you have in the trie is 2 times 10 to the power of 4. Then each of the folders depth, that means you write /a/b. So how many strings you write after slash, that is the depth. So let's call this as m. So your m is maximum 500. That means the depth of the trie will be maximum 500, and the number of nodes in the trie, n, will be less than equals to 2 times of 10 to the power of 4. And each of the string here that you write in this, all the examples you have seen A, B and so on, right? But it can be in the form of a string. Like let's say cat can be a node, cat can be a folder name, but each of the folder name should be less than equals to 10 size. So how many characters can you have exactly? So you will see that this is the depth and this is the number of nodes. If you multiply the number of nodes with the depth, it is coming out to be 2 times of 10 to the power 4 multiplied by 500 and multiplied by the number of characters in each of the string. So that is going to be 10. And if you see, this will be 10 to the power of 8, where 4 plus 1 5, 5 plus 2 7, and 5 2s are 10. So this is 10 to the power of 8. This will be taking 1 second or even more than that. So this can give you TLE if you solve using an order of NM approach, right? So this is the proof of it. But the next constraint is interesting, where it says that the sum of all the characters, that means sum of all the paths at ij.length, is less than equals to 2 times of 10 to the power of 5, which means that it is not 10 to the power of 8, but it is less than equals to 2 times of 10 to the power of 5. So it is well within the 1 second range, because it is well within 10 to the power 8 range, right? So this fourth constraint is very important, and this says that I can solve it with NM algorithm. There is no problem. I can solve it with NM log n, NM log m, whatever, and it will not create any problem. Paths at ij consist of all the lowercase English letters only from A to Z, and no two paths lead to the same folder. And for any folder not at the root level, its parent folder will also be in the input. That means all the paths are absolute path, which starts from the root node /, right? So I hope the problem statement and the constraints are clear. Now let's look at the concept of serialization. If you have already seen 297, then you will know it. Or otherwise you can just see it as a recap how to serialize a binary tree. Let's look at the first tree. In this case, if I just apply simple DFS and try to flatten the tree side by side in the form of a string, then you can take AB and then you can append BA to it. And if I follow the same process for the second tree, then I can append A, B, BA. Now if you compare both these strings, then they will look the same. Both the strings are same, but the structure is not same. These two structures are not same, but the flattened strings are same. That means the serialization is not good. It is a lossy serialization. Lossy, that means we will lose information if we do this. It is conflicting, lossy and conflicting. Okay. So we can simply use a separator, because the problem has happened because there was no separation between the values. Because how will you identify between ABC if the nodes have 3 values A, B, C? Or do they have only 2 values A, B, B, C, or A, B, C? What is the approach? Or does it only have a single node called ABC? You will not know, right? Unless you use a separator. If you put a separator, then it will be extremely clear what is what. So we can go for comma separator, multiplication or bracket. So simply go for comma and these two strings will be different now. In this problem, you will not need to deserialize. That means you will not be required to take this string and again get back the exact structure of the tree. And that is why we do not need any idea for deserialization. Otherwise, if you have seen 297, then for deserialization and getting the exact same structure of the tree, you should also maintain where are the null pointers. Okay, so you should have another separator for the null pointer so that you can generate the exact exact unique tree from where you got this serialized string. But in this case, in this problem, deserialization and exact reconstruction of the tree is not required. So we will only use the serialization technique. Okay. So for more details, look at the video 297. Okay. Now if you have understood this, then let's see how to build the trie and serialize using DFS. So all the absolute paths will be given. These are all the paths from the root node. Okay. Now once you see any path, you start with a slash and start inserting in a trie. You watch my video on trie if you have any difficulty here. So start inserting in the trie. This is the trie node structure which I have already made. The root node will be present by default right from the beginning. I will create it. So each of the trie node contains the folder which will be storing the string name. Then a boolean remove, because I need to find out what all structure in the trie has to be removed, which are actually redundant, isn't it? So for marking what all I have to remove, I will be keeping a boolean flag that I will show you later how to use. Now I will also use a map which will keep track of actually what all structures have I already seen, so that I can see a duplicate structure and make out that okay, I have seen that structure. So this also will be shown on the next slide. Here I will just be constructing the trie. Okay, and this is the constructor of the structure trie node, where if you create a new object of the structure, then you can pass the folder name and it will be assigning to this folder name, right? So now let's do it. We do not have a node 2a, so make node a. Now insert ab. So from root node you already have a, so get b. That's it. Now insert abx. At the root node you already have a, you already have b, then insert x. Okay, you are done. Insert b. From the root node you don't have b, so insert b. Now after b, you look at ba. So from root node you have b, insert a. You now have ba. Insert bx. Now from the root node you have b, but you don't have x, so insert x. Now insert w. From the root node you don't have w, so insert w. And insert wx. So from the root node you have w, but you don't have x after it, so insert wx. Okay. So this is how the trie insert will happen. Now this is step number 1. Step number 1 is to do trie insert, and trie insert has been done. Now after doing the trie insert, step number 2 is to serialize. Okay, serialize it. So how do you serialize it? Step number 2 also have deduplication, but I will be showing you that on the next slide. How do you serialize it? Now if you serialize and follow the previous approach, you can do it with DFS, but instead of using comma separator, I will be using the bracket. Okay, by the end you will understand why brackets are making more sense instead of comma. But let's first do the serialization. I will be following the post order traversal, so that all the folders below a certain folder, like let's say below B, every one will be represented in this way, A and X. It will come inside the brackets and then only B will be appended to it and it will be shown in this way. So this can only happen if you do post order traversal. That means take all the subfolders together, combine them in the form of a string and then append the current folder name. That's what I will be doing. You can also go for pre-order traversal, whatever makes sense, you can take that, but I have taken post order traversal. So in this case you can start from the root node and then you can go to A, you can go to B, you can go to X, right? At X you cannot make any other call, so what will be returned? It will be bracket current folder. What is the format? First you put a bracket and then you put the current folder name, then you put all the subfolder names, but the subfolder at X do not have anything, right? So it will be empty, and then to this you append a closing bracket. This will be the format that I will be using, and so X with brackets is sent to B. Now from B there is no other branching. So what it will be returning, it will take x and it will append b in the beginning. Now you can append b in the beginning or at the end, it is up to you. So I will be appending in the beginning and put 2 brackets according to the format and send to a. Now at a you do not have any other branching, so what you will send, take the return value bx and append a in the beginning and return it with brackets to the root node. Now the root node will not be appending it right away, but it also has a path to b. So it will explore b, it will explore a, and this a will return a inside bracket. Now b will explore this x and it will get x inside bracket, and then b will be appended to a and x, and this will be the return value to this root node. Now this root node will be calling w, w will call x, x will be returning this x inside bracket, this w will be returning w appended to x in this way to this root node. Now this root node having explored all the possible path, it will take all of them and append side by side, like a will be appended, okay, and then this one b will be appended with a and x, and side by side you will be appending this w. So I don't have any space on the right side, so that's why I'm writing below wx, and in the beginning you will be taking a root node slash and you will be appending it in this way. So this will be the format that I will be using. Using post order traversal, you can create this kind of serialization. Now why this makes sense instead of using comma? In this case you can easily make out that when you go from left to right, then you remove the first bracket and the last bracket, then you know what all nodes are at the top level. The top level will always have one node, which is the root node. Then whatever set of brackets you see, this a starting from a, starting from b, and starting from w, all these will create 3 different branches. 3 different branches, one starting with a, one starting with b, and one starting with w. And likewise, if you see internally, then 1b means that this a has another b branch, and that is only the single branch. Okay, this b has 2 branches to a and x, right? So that is how you can make it out, and this is very easy to read. If you just put commas, then it will be difficult to identify where is the closing bracket and where is the opening bracket, right? That means where the level is ending. You can't just put the same operator, because if you put comma, you will not realize where the level is starting and where the level is ending. So that's why we need 2 separators, and it makes sense if you take some kind of opposite separators. That means opening bracket, closing bracket, anything would be fine, right? So that would be reasonable. So this is how I will be serializing. Now in step 2, I will not just be serializing, but I will also be doing deduplication. Okay, so let me show you how to do deduplication. So I have already done step 1. That means from the list of absolute path, I will be constructing a tree or the trie, and the trie is already made. Step number 1 is already done. Step number 2, I will be doing serialization along with deduplication. So in case of deduplication, I have to remember what all paths I have already seen, so that if I see them again, then I can mark that, okay, I need to remove it. And in order to do that, I will be using a map. So the key part of the map is going to be the path, the absolute path in the form of the string name, and the value path will be the exact trie node. That means what is the address of that trie node. Why this is stored in this way? Because let's say in this case, if you see wx and this bx are repeating. Okay, so when you go to bx, then you will not realize that another wx which is identical is also present. You will not realize that. You will realize it only when you go in DFS and reach to this w and say that, okay, since here you have wx and I have already seen a bx which is similar, right? So I have to also not just mark this w as, okay, remove this structure, but I have to also remember that I should be removing the previously occurring same structure, which is b. So the reference of b has to be stored in the map. Otherwise, how will I know where it occurred? If I tell you that this is repeating, then yes, you can remove it, but you have to also remove the repeating one. That means the identical one, wherever it is present. So the location has to be saved in the map, and that is why I will be using value as trinode star to store the location. So let me show you how to do this, okay? So I will be building a map where string will be containing the path, and the trinode star, which is the location, will be stored in the value part, okay? Now let's start. So I will be starting with the slash here, and then I will be iterating on all the paths. Simply I will be applying DFS using the serialization method. So I'll go to A, I'll go to B, I'll go to X, I'll go to Y, and Y will be returning this brackets, okay, bracketized Y. Now at X you don't have any other path. So what is that you got as a return value? Y. Is it present in the map? No. So you are seeing it for the first time, so save it and then say that it occurred at node X. Now what will this X return? It will be returning X, Y, okay, and this value got at B. Now B will be checking here, is this XY seen? No, it has never been seen. So that's why I will be saving it as X, and then I will be having Y here. So save it and say that it has occurred at B. Now this B will be returning B, X, Y, okay, and it is now received at A. So A will be checking if BXY has occurred. No. So it will be saving BXY, okay, BXY, and it will say that it has occurred at A. Because A do not have any other branch, it will not wait. It will return that value appended by A, B, X, Y, Y, X, B and A. Okay, so this has been received at the root node. So the root node will not directly check this because it has other branches to consider as well. So it will be going to B, B will be calling to A will be returning only A. So has A occurred? No, it has not occurred. So it will not immediately save because from B there is another branch to X. So it will go to X and X will return X. So at B you have AX. So has AX occurred? No. So you can save AX and say that it has occurred at B. Now this B and this B are different. Okay, they are tri-node star type, so they will not be identical. They will say the exact node. So what this will return? It will return B appended to AX. Okay, so that has been reserved at the root node. Now the root node is making call to W makes call to Y will be returning Y in bracket. So W will check as in Y in bracket has occurred. Yes, it has occurred. So if it has occurred, where it has occurred? It has occurred at X, so it will get the reference of X. So mark the remove pointer. That means you have already seen the remove pointer here. That means the remove boolean. It will be set to true. It will be by default false, and you need to set to true. So remove will be set to true here, and remove will be set to true here. Don't do anything, just set to true and return the value. What value will it be returning? It will be returning W with Y. Okay. Now the root node is receiving this from one side with B and with W. It will append all of them and check in the map. It is not present, but anyway you are done. You are at the root node. You don't need to do anything here, right? You are done. After completing the process, your step 2 is done. Step 1 was building the try build. Step 2 was doing serialization, serialize, plus you have done deduplication. That has been done now. And the step 3 is in step 3 simply you have to run the cleaner. How will the cleaner run? The cleaner will be running with the DFS. So you can maintain a stack, or simply you can say that I will be maintaining a array. You can maintain a stack or a path list, and you can push the root node. The root node will be slash. You can push it or you cannot push it. The return value anyway is not going to have it. So this will be the current path. You can say this will be the current path. Now I will be maintaining a result which will be storing all the paths, and when you go to A, you check the remove pointer. The remove value will be false here. Okay, so if it is false, save A into the path and push A into the result. Okay, so this is one path. Now you go to B. Remove value is false here, so append B to the list and append another path A comma B into the resultant path. When you go to X, its remove value is true, so immediately go back. You don't need to parse this. This is trimmed now. From B there is no other path. From A there is no other path. From root node there is a path to B. So go to B. At B the remove value is false. So when you had gone back, when you had backtracked, you have to remove it from the current path. And when you go to B, the B will be pushed, and so B will be a new path. Okay, from B you go to A. Here also remove value will be false, A will be pushed, and BA is a new path, B comma A. Then you will be backtracking, so pop A, and from B you will be going to X, so push X. Now your path is BX because the remove value is false here. Now you backtrack from X, backtrack from B, backtrack from X, backtrack from B. Now the list is empty. You go to W, push W. W's remove value is true, so it will not be pushed actually. Since its value is true, I don't need to parse it, it's done. And you will backtrack, and from the root node you will backtrack, and this will be the all possible absolute path after removing the identical subfolders. Okay, so I hope this entire technique is clear. Now in this case, if you assume total number of folders to be n, and I will say that each of the path length is w, then I will say order of n w. And if I have taken a ordered map for maintaining these child pointers, I have taken ordered map, then you can assume that I will be taking log of n, which is the total number of folders in log order, because lookup in a ordered map will take log n time, and all the nodes can be just at the next level, and that is why I will take all the nodes in the worst case log of n. This is your time complexity, and your space complexity is going to be order of nw, because all the words have to be stored in the trie. So the time complexity is nw log n, and the space complexity is nw because of the trie construction and the map size. I hope it is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this code, we will first define the trie node structure. So this I had already explained you. In the trie insert, I will be getting each of the absolute paths one by one, and I will iterate through each of the folder names, and if the folder is not already made, then I will make it and assign it to the child pointer, and if it is already made, then I will just be going down and skip making a new node. Okay, so this is how you do simple trie insert. Now if you look at the main function, then the step 1 was to create first the root node and then insert all the paths into the trie. So step 1 is done. Step 2 is mark the repeating paths. So we can take a visited map for it, and we will be marking all the identical substructures. So how that is done? We already know how to do this by using simple DFS. So we'll be starting at the root node, and I will have the visited map. So I will be calculating the combination of all the subfolders. So this subfolder after this line here will contain that if you were present at any point, like let's say if you were present at A, then at A after running, the subfolder will contain B, X, Y with all the bracketization. That is what the A will contain here. Okay, so if the subfolder.size is empty, which means that you were at the leaf node, then in that case only it can become empty. So if it was a leaf node, then I will be simply appending the brackets inside the root folder and returning. If you remember, at Y I was not doing any checks. I was just returning Y inside the bracket. That's it. So only for the internal node these two cases will run. In the internal node, I will be checking if I have already seen such substructure. That means when I was at W and I got the return value here, then it was Y. So Y was already seen at X, and that is how I know that it is identical. So it is asking about, is this current node identical to somebody? And if it is identical, then mark the remove as true, and also mark it true for the node where you had seen it using the map. So mark it true at this point wherever you have found identical, and also use the map to see the location, track the location where it was identical, and that remove should also be marked as true, right? So both those nodes will be marked as true to be removed later in step 3 by the cleaner. Otherwise, if you are seeing it for the first time, then save it into the map. Save it into the map with the current nodes reference. So that is what will be done. So this is step number 2, which is about serializing and also deduplication, you can say. And the third step is about saving the path after deletion. So I will be taking a 2D list, which is result, and a current path list, and simply iterate for each of the branching from the root node. So what is this? If you start from the slash, then it is saying start with A, start with B, start with W. So that is what is root at child. Okay, and try to save all the paths that does not come under the flag remove equals to true. So simply you start, and if the current node's remove value is true, then just return back. So that means we are trimming it. Otherwise, you push the current folder name into the current path and save the current absolute path into the result, and simply iterate for all the child pointers, okay, saving the path. And once you come back, when you backtrack, before backtracking you remove the current folder name from the current path. So this I have already shown. So this is the simple DFS approach using serialization and deduplication, and I hope it is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.